From here on out in this chapter, we're going to be discussing probability. Section 11.4 is on the fundamentals of probability. When we talk about probability, there are two main types. The good news is that the process of finding probability is very similar regardless of what type of probability you're looking at. The first type that we're going to encounter is called empirical probability, and I put some keywords in red below it. Words like frequency, observations, because empirical probability is the relative frequency of occurrence of an event and is determined by actual observations of an experiment. So what will happen is the question will say, based on these observations, now find the probability that such and such event occurs again. So it's very much based on observations. Just section 11.4 is going to have empirical probability. Then section 11.5 on, the remainder of the chapter will focus on something called theoretical probability, which is not based on observations, but rather I have keywording in blue is the study of possible outcomes. So it's determined through a study of the possible outcomes that can occur for the given experiment. So this is where you're going to see such examples like a deck of cards, a standard deck of 52 playing cards. Find the theoretical probability. If you draw one card, you draw an ace. So it's not based on observations. You would have to know all the outcomes. You'd have to know what's on a standard deck of playing cards. You would have to know that there are 4 aces in a standard deck. Theoretical probability would be rolling a dice. You would have to know there are 6 sides on one die. So starting with empirical probability, it says the empirical probability of an event, and notice I use capital P for probability, and whatever I want to find the probability of, I put it in parentheses beside the P. So in this case, this is read out loud as the probability of event E. So I'm going to put words in the parentheses. This is not like algebra. In algebra, it would have been P times E. We're not multiplying here. This is the notation for probability. Probability of something happening is determined by the following formula. So you're going to figure out the number of times that event they're calling E has occurred, and then you're going to divide it by the total number of times the experiment has been performed. The key words in this formula to me is whatever's in parentheses that I'm trying to find the probability of, that's going to be reflected in the numerator. So I just simply have an E in the formula, so you have that capital E again in the numerator, and then the grand total most of the time is in the denominator. So my little memory trick for empirical probability and even theoretical probability is whatever they're asking you for, so whatever the problem wants to find, and you divide that number by the grand total. And there are going to be some exceptions to this formula later in the chapter, but most of the time, this is what we're looking for, what we want, in other words, what the problem's asking us for, divided by grand total. If you do not see directions that say round, it means that it wants your final answer as a simplified fraction. And there is a button on your graphing calculator that will reduce fractions for you. The probability of an event, regardless if it's empirical or theoretical, is always a number between 0 and 1. So what that means is if you're finding probability and you get an answer bigger than 1, you've done something wrong. Or if you get a negative number, you've done something wrong. Let's look at our first example. So it says a pharmaceutical company is testing a drug that is supposed to help reduce high blood pressure. The drug is given to several individuals with the following outcomes. Blood pressure reduced, 379. So it actually worked. The medication worked with 379 people. Blood pressure unchanged, 62. So the medicine didn't help but didn't hurt their blood pressure. Blood pressure increased 59. So 59 people, the medication actually made their blood pressure worse. If this drug is given to an individual, determine the empirical probability that the person's blood pressure is A, reduced, and part B, that it's increased. I've circled that phrase, empirical probability. Remember, empirical just means that we're going to get our final answer by looking at previous observations, which they've already provided for us. And what's nice is they literally say find probability. So that keyword there. And most of the time that means we're going to look for what they want in the original question, and we'll divide by the grand total. Then we'll see if that fraction can be simplified, and that will be our final answer. So starting with reduced, probability of reduced blood pressure equals what we're looking for. That's what I mean by what we want. That's always going to be reflected in the numerator. So reduced, they tell you 379 people had reduced blood pressure. Divided by the grand total, they did not give us the grand total, but it's easy enough to find. I'm going to simply add up all the outcomes. So 379 plus 62 plus 59. Add those numbers all together, and you should be getting 500 total people were observed in this study. So 379 reduced blood pressure out of the 500. Now, before I type this answer into the My Math Lab homework, I'm going to check in my graphing calculator to see if this fraction will reduce any further. So to check if a fraction can be reduced on the calculator, let's begin by typing it in. So that was 379 divided by 500. We're going to use our favorite button for this chapter, the good old math button here. And it's already highlighted on frac for fractions. You just press enter again. The word frac, the abbreviation frac for fraction, comes onto the main screen, and I hit enter a second time. Because the fraction comes back to me, not reduced at all, that tells me that the fraction is already reduced. 379 over 500 is as simplified as it's going to get. It doesn't hurt to check every single fraction, especially come test time, just to make sure it doesn't reduce any further. So again, type it in. Remember, fraction just means division. Math button, enter twice. So just think math, enter, enter, and that will tell you if your fraction can be reduced. So I'm going to leave 379 over 500 as my final answer. Part B, we're looking for the probability that the drug actually increases the blood pressure even further. So we're looking for increased. That part we're looking for always goes in the numerator. Increased blood pressure, well, there were 59 patients in this particular study that had increased blood pressure from the drug. Divided by the grand total, 500. Let's go ahead and check again. Doesn't hurt to check in the graphing calculator using our math button, enter, enter, just to see if this fraction will reduce any further. Checking on the calculator, I'm going to type in 59 divided by 500, math, enter, enter, and I get back the same exact fraction, which tells me it's already simplified. So that's the final answer. So I'm going to circle that final answer of 59 over 500. Let's take a look if we can find an example of a fraction that will actually reduce. That way you can see what that will look like on the graphing calculator. So let's go ahead and just pretend there's a part C here that asks us to find the probability that the blood pressure remains unchanged. So the number of unchanged, 62, divided by the grand total, which is still 500. This fraction will reduce because I'm seeing even numbers on the top and bottom. I'm going to go ahead and type in 62 divided by 500, math button, enter, enter, and this one reduces down to 31 over 250. So it looks like the top and bottom were just divisible by 2. So 31 over 250. I'll go ahead and write that as the final answer. 31 all over 250. Looking at another example, if one person is randomly selected from the population described in the following table, find the probability expressed as a decimal rounded to the nearest hundredth that the person A has never been married, B is male. So as I look at the table provided, it's giving me marital status of the U.S. population ages 15 or older in the year 2010, and all of these numbers you see in the table are in millions. Whenever I encounter a table in this chapter, my first instinct is to just make sure they gave us all of the totals, because if they didn't, we need to take an extra minute and add everything up ourselves. Luckily, in this first example with a table, we have totals in both directions. So when they give us totals, let's keep in mind that the grand total number of people surveyed will be in the bottom right corner right here. Technically it is in millions, so this is 242 million. Starting with part A, let's find the probability that the individual had never been married. What we're looking for, never married, should be reflected in the numerator. So it does not specify men never married or female never married, so it must want the entire never married column in this case, which is right here. Here's the never married. So 74 never married, that's the statistic we're looking at. Always divide by grand total, that was 242. So technically this is 74 million divided by 242 million. I don't need to write the million because it's going to reduce to the same fraction regardless. And however, it doesn't want the fraction for a change because the directions say expressed as a decimal rounded to the nearest hundredth. The hundredth spot is 2 digits out. Let's go ahead and type this into our calculator. So 74 divided by 242, hit enter. I get a decimal where the calculator has to cut it off. It's a decimal that never ends. So it's 0.305785124. We only care about the digit after where I want to round to. So if it's 0.305, the 5 means we should round up. So the 0.305 is going to round to 0.31 to the nearest hundredth spot. It's up to you if you want to put the 0 in the whole number spot or not. In science courses, they will have you put that 0 there just to emphasize the location of the decimal point. So approximately 0.31, which if you converted that to a percent is about 31% of the people surveyed had never been married. Now let's take a look at part B, probability that a person surveyed here is male. So now I'm going to look across the row. It doesn't specify just the married men, just never been married men, divorced or widowed, just any of the men surveyed. So that's 118, technically 118 million. What we're looking for is the numerator every time. Divide by grand total is still 242, technically 242 million. Let's type it into the calculator. 118 divided by 242. Again, it's a decimal that never ends, so the calculator has to round the last digit that it can hold. The directions still say nearest hundredth. So if I look 3 spots out, it's 0.487. That 7 means round up. So I'm going to round 0.48 up to 0.49. So roughly 0.49 or 49% of the population surveyed were men. Taking a look at our first theoretical probability formula, it looks a little different, but the good news is that it's the same pattern as when we found probability for empirical probability, that is. Looking at the textbook definition, if an event that they're calling capital E has something called equally likely outcomes, the theoretical probability of an event E may be calculated by, so we're going to use P for probability of event E. So what you want to find is going to still be in parentheses. You're going to take the number of outcomes favorable to E, and you're going to divide that by the total number of possible outcomes. So why I say it's the same process as finding empirical probability, well, what we want to find, meaning what the question asks us for, is still reflected in the numerator. They're asking for event capital E, and we see that again in the numerator, divided by, and the bottom will still be the grand total. And as I mentioned before, there are exceptions to this rule, which we'll see near the end of this chapter, but most of the time the grand total will be in that denominator. When we talk about equally likely outcomes, for example, if I roll some dice, as long as those dice are not weighted, I have the same chance of rolling a 1 as I do a 2, a 3, a 4, and so on. So whenever you're dealing with something that has the same likelihood for each outcome, you can use this formula. Looking at example 3, it says a die is rolled. Whenever they say die, that refers to one dice. So that's dice singular, die, D-I-E. Determine the probability of rolling the following. And I have 4 parts, A through D. Let's start with part A. So the probability of rolling a 5. Now this does require a little bit more thought than empirical probability did, because I have to know how many sides on standard dice have a 5 on them. So standard die would have 6 total sides, and they would have each number with spots, with dots traditionally, on each side. So I would need to know that there is 1 5 side. So what we want in the numerator, we want to roll a 5. There's 1 5. Divide by the grand total, where there are 6 total sides. This fraction is already simplified, so 1/6 is the final answer for part A. Let's just draw that 6 a little bit better. Okay, so 1/6. B, now it wants the probability of rolling an even number, so we have to know which even numbers are on standard dice. Well, 2, 4, and also 6. There's a 2 side, a 4 side, and a 6 side on standard dice. So counting this up, 1, 2, 3. 3 outcomes have an even number on them. That's what we want. Divide by the grand total number of sides. There are 6 total sides. Now, this is a fraction that's easy enough to simplify in our heads. Obviously, this is going to simplify to 1/2. But this is a great opportunity to practice finding the math simplifying buttons on the calculator so that we're ready to go when we get yuckier fractions to simplify in the homework and on the tests. So, taking a look at our graphing calculator, if we wanted to simplify 3/6 in the calculator, I type in the fraction as normal. So remember, fraction bar just means division. So 3 divided by 6. I hit our favorite button, the math button. Third one down on the left side, it's below the alpha button. So math. And then hit enter twice. Math, enter, enter. And I know there's a little bit of a glare here, but as you can see, bam, it simplifies down to 1/2 as the final answer. So that's the final answer to part B, 1/2. Looking at part C, remember this is all the same example, example 3. It says, what's the probability of rolling a 7? Well, that's impossible. There are only 6 different numbers, the numbers 1 through 6, on standard dice. So anything that's impossible, the probability answer will always be 0. So 0 represents in probability something that it will never occur. If I roll some dice, some standard dice, there's no way I'm going to roll a 7 on one die because there's not a 7 side. Looking at part D now, what's the probability you roll a number less than 7? Well, what we want, a number less than 7, well, all 6 numbers on standard dice are smaller than 7. Divide by the total number of sides. There are 6 total sides. 6 divided by itself is 1. And if you think about it, it makes sense because 1 represents the answer and probability of something that will definitely happen. So without a doubt, this will definitely occur. If I pick up some dice, if I roll one die, I'm guaranteed a number smaller than 7 is going to appear. Example 4 says a card is selected from a standard deck of 52 playing cards. Determine the probability that the card selected is a 7. Card is A. And then this question is actually A through F. We need to make sure that we're familiar with the cards in a standard deck of playing cards. What you can do is I've uploaded a handout with a picture of all 52 playing cards on it into your course. Go ahead and locate that handout. Feel free to print it out with a color printer. And you can actually use that handout come test time. So you can bring it with you to the testing center and use it on the test. That way, you don't have to memorize all the cards if it's been a while since you've used playing cards. I'm going to go ahead and bring a picture of that handout onto the screen so we can talk about those playing cards you would see in a standard deck. So here you can see all 52 playing cards. Notice there are no jokers in a standard deck in the homework. What's unique about the homework and possibly test questions is that the aces are considered a low card. So pretend the aces have a value of 1 on them. That's why I have them below the 2s or before the 2 cards on this handout. As you look through these cards, each row we call that a suit. So the first row is the suit of clubs. You can see that there are 13 cards, by the way, in each row. Therefore, there are 13 cards in each suit from ace to king. So we have 13 clubs. The second row shows that we have 13 of the suit of hearts. The third row shows that we have 13 of the suit of spades. And the last row shows that we also have 13 of the suit of diamonds. You'll notice that half of the cards are red cards. The other half of the deck is comprised of black cards. We have 13 clubs plus 13 spades, which makes a total of 26 black cards. We also have 13 hearts plus 13 diamonds, which also makes a total of 26 red cards. The homework might refer to what they call picture cards. Picture cards are also known as face cards. So those are literally what have a picture of a face on them. So jacks, queens, and kings, this is what they mean by picture cards or face cards. Notice I do not include the aces as a picture card. We have 4 jacks plus 4 queens plus 4 kings for a total of 12 picture cards, 12 face cards. Going back to our question, part A, the question asks us to find the probability of, if you draw a card, getting a 7 card. As we look at our picture, we see that there are 4 7 cards. We got the 7 of clubs, the 7 of hearts, the 7 of spades, and the 7 of diamonds. So what we want, a 7 card, there are 4 of them. Divide by the grand total number of cards, which are 52. Do not type that as the final answer. You always need to check first if your fraction will reduce. So we're going to go ahead and type that into the calculator, that 4 over 52. We type in 4 divided by 52, math button, enter twice. Final answer is 1 over 13. By the way, you might have already noticed this. If you forgot to hit the math button and you just hit enter, you get the decimal. Even after the decimal appears, you can still hit math button, enter twice to get 1/13, the simplified fraction formatted answer. I'm going to go ahead and write down 1/13 was the final answer to part A, the probability of drawing a 7 card. Looking at part B, what's the probability we draw not a 7 card? Not means anything but. So if I take away those 4 that are 7 cards, we had 52 total cards minus the 4 that were 7s, leaves us with 48 cards that have anything but a 7 on them. Divide by the grand total number of cards, which is 52. Go ahead and reduce the fraction either in your head or on the calculator. After you do so, you should be getting 12/13, 12 over 13, as the final answer to B. C, what's the probability? This is all the same example. C is the probability that that one card you select happens to be a diamond. Well, the diamonds make up the bottom row, and we said each row, each suit has 13 cards in it. So we got 13 diamonds. What we want, divide by grand total. We wanted diamonds, divide by grand total. There are 52 of them. 13 over 52 will reduce. If you want to type it in the calculator, math button, enter, enter. You should be getting 1/4. Go ahead and check it. But 1/4 is going to be the final answer. If you think about it, that makes sense because the diamonds make up one suit out of the 4 total suits. They make up one row out of the 4 total rows. Now I'm looking at D, the probability that that one card you select is a picture card, aka also known as a face card. I already mentioned earlier that whenever they say picture cards in the My Math Lab homework, they're referring to the jacks, queens, and kings. So if we want a picture card, there are 12 of them because there are 4 jacks plus 4 queens plus 4 kings. So what we want, picture cards, 12 of them, divide by grand total is still 52. Go ahead, reduce, reduce, reduce. After you reduce, you should be getting 3 over 13 as the final answer to part D. Part E, the probability that that one card you select is a heart and a spade. We have to be really careful with the wording in all of these probability questions. This is a commonly missed question. A lot of times, people will say, okay, well, there are 13 hearts plus 13 spades, so that's 26 over 52 reduced. No, no, no. You would use that strategy if it had said the word or. In other words, if that one card you randomly selected was a heart or a spade, then yes, you'd add them up. But with the word and, you're only drawing one card. So the word and refers to a card that meets both qualities. In other words, and means at the same time. So if you're drawing one card, what's the probability that it has both a heart and a spade on that card at the same time? Well, that's impossible. That doesn't even make any sense. You cannot have two suits at once on a card. Anything that's impossible in probability, you'll get a final answer of 0. It's technically 0 divided by 52 total cards, but that reduces down to 0 anyway. So whenever you're reading a probability question and you go, that doesn't even make any sense, that's impossible, final answer is 0. Finally, looking at F, what's the probability that that one card you select has a value less than 4 on it? Keeping in mind that we're pretending the aces have 1s on them, since ace is treated as a low card, everything less than 4 would be the aces, since those are 1s, the 2s, and the 3s. It does not say or equal to 4, so I'm not going to include the 4 cards themselves in the count. So we have 4 aces, plus I have 4 2s, plus I have 4 more 3 cards. 4 plus 4 plus 4 means 12 cards have a value less than 4 on them. Divide by the grand total number of cards, which is still 52. Now reduce 12 divided by 52. Math button, enter on the graphing calculator. You should be getting 3/13. If you reduce that in your head, the top and the bottom numbers are divisible by 4. But either way, 3/13 is the final answer to part F.